Swayam Prabha. Digital India. Educated India.
Vertical alignment part 2. In lesson 13 we discussed about design of vertical alignment, particularly the design of summit and valley curves following IRC approach or Indian Roads Congress guidelines. After completing today's lesson, the student will be able to appreciate the control grades used for design of vertical alignment as per AASHTO, American Association of State Highway and Transport Officials. Student will be able to understand the basis for calculation of critical length of grade, again as per AASHTO approach, and students will be able to design summit and valley vertical curves following AASHTO approach. The IRC approach we have already discussed or covered in lesson 13. So, after today's lesson, student will be able to design vertical summit and valley curves following AASHTO approach. The AASHTO recommendation about grade, what should be the maximum or minimum grade, that is basically based on vehicle operating characteristics on grades. It is observed that almost all passenger cars can readily negotiate grades up to 4 to 5% without much reduction in speed. That means, if the grade is up to 4 or 5%, it is generally acceptable to cars, they do not face much problems. Now, what happens if the design vehicle is a commercial vehicle or a truck instead of a car? Now, the effect of grade on speed is more pronounced in case of cars, in case of trucks than on passenger cars. Obviously, maximum speed that can be maintained by truck depends on length as well as stiffness of grade and the truck's weight power ratio. So, generally the effect is more pronounced on truck. Now, let us see the graph how the truck speed is reduced. Look at the graphs. Here it is shown that at various grades, longitudinal grades, how the speed is reduced over distance. It is clearly observed that more the grade, more is the reduction in speed, and also the speed generally reduces more as the distance is more. Now, keeping this in mind, that means commercial vehicles, particularly when they negotiate grades, as the distance is more, there is a reduction in speed. Keeping that phenomena in mind, the grade upper limits are decided. Now, sometimes the design vehicle is a recreational vehicle, but this consideration is not critical except on certain designated recreational routes, where special type of recreational vehicles are taken as design vehicles. So, based on the vehicle operating characteristics, the control grades for design are recommended. There are two types of limit, one is the maximum value, the other one is the minimum value. There is what should be the minimum grade. Now, the maximum grades, let us have a look at certain salient features or the points. About 5% grade is recommended for design speed of 110 kilometer per hour. So, if the design speed is up to 110 kilometer per hour, 5% grade is acceptable. Now, as the speed is less, obviously steeper gradient can be used. So, the gradient may be in the range of 7 to 12% if the design speed is around 50 kilometer per hour. Now, obviously, for design speed in between, that is 60 to 100 kilometer, the grade will also vary between the above two extremes. We should try to provide flatter grades as far as possible. The maximum allowable grade should not be used all the times for design. We should try to provide flatter grades, keeping the maximum grades for extreme situations, where terrain condition is difficult, site specific problems are there. So, we should try to keep the extreme values for those cases. Now, there are certain relaxation, say for short stretch less than 150 meter and for one way downgrades, the maximum grade may be about 1% steeper than other locations, and if it is low volume rural highways, it may be more by about 2%, it may be 2% even steeper than other location. So, for short stretch, if it is the length is less than 150 meter and for one way downgrades, the maximum grade may be 1% higher in general. For low volume rural highways, it may be even 2% steeper. So, that is a relaxation which is available or allowed or permissible in the design standard. Now, let us look at the other extreme, that is the minimum grade. Now, with curved highways, minimum longitudinal grade of about 0.3 to 0.5% should be provided to facilitate surface drainage. Obviously, what should be the exact grade between 0.3 to 0.5%, that will depend on the type of pavement. Now, why this minimum grade provision and why it is for curved highways? Now, for curved highways, the water cannot go directly to shoulders, because the curves are there, roadside curves are there. So, the water cannot go directly on shoulders. That is why there is a slight longitudinal grade that should be provided, so that the the water can flow in a desirable manner or in an acceptable manner to the water inlets. In that type of situation, particular attention should be given to the design of storm water inlets and their spacing to keep the spread of water on the travelled way within tolerable limits, because not that at every point water can or directly go to the shoulder. So, it has to go on certain designated water inlets. So, appropriate slope should be provided, so that water can go easily to those inlets, and the spread of water is done in a controlled manner. That is what justify the need for the minimum grade. it may be recalled that when we discussed about the Indian Roads Congress guidelines, there also we talked about the minimum longitudinal grade, but the reason why IRC recommends a minimum grade wherever topography permits, and the reason why a minimum grade is recommended for carved highways as per AASHTO, they are not really identical. The basis is different. That is to be understood and kept in mind. Coming to the critical length of grade for design. Now, we have talked about the maximum grade, but maximum grade itself is not a complete design control. Length of a particular grade should also be considered for desirable vehicle operation. This is purely based on the fact that if the length is more, as the length is more and as the grade is also more, there is a reduction in speed. We have already seen the trend earlier. And if it is heavy commercial vehicles or the commercial vehicle proportion is significant, or if the design vehicle is commercial vehicle, then there may be significant loss in speed or significant reduction in speed. So, therefore, to have the overall operation within desirable limit, it is also necessary to specify the maximum length of grade. For different grade, what should be the maximum length at a stretch to keep the vehicle operation, overall vehicle operation within desirable limit. Now, to maintain wherever it is difficult to or the freedom of movement or the freedom of operation on grades longer than critical. So, obviously, there will be loss of in freedom of movement. Therefore, suitable design adjustment such as maybe changes in location to reduce grade or addition of extra lanes should be considered. That means, wherever the length is becoming more than the critical length, there in those locations suitable adjustments are to be made, extra efforts are required to bring the operation within desirable limits. Now, let us try to then formally define what is critical length of grade. We have already discussed, but let us try to define it now. Maximum length of a designated grade on which a loaded truck can operate without an unreasonable reduction in speed is critical length. That means, it is that length, maximum length for a given upgrade where a loaded truck can operate without unreasonable delay or reduction in the speed, without unreasonable reduction in the speed. So, we try to limit the length, and that is what is the critical length of grade. Now, to establish design values for critical length of grade, several assumptions are required. Number 1, size and power of representative truck or truck combination to be used as design vehicles, along with gradability data, that is weight power ratio. A typical value is maybe 120 kg per kilowatt. So, we have to specify the size and power of the representative truck or the truck combination what we are trying to use as design vehicle, and the gradability data, particularly weight power ratio becomes critical. Then it is also necessary to mention or to define the entry speed, which may be taken as the average running speed on planes. Then maximum or then the minimum truck speed below which interference to following vehicle is considered unreasonable or annoying to the following driver. Now, obviously, if on a grade a commercial vehicle is moving and there is a continuous reduction in speed. So, particularly for two lane roads, sometimes other vehicles which are maybe cars or other light type of vehicles, they are forced to follow this slow moving vehicle which is moving at a much lesser speed. So, it becomes annoying to the following driver to follow a slow moving vehicle for a much longer time. Obviously, what is annoying, that will depend on the design speed for which the road is designed, or the road is designed to accommodate certain design speed. So, what is the speed, that is minimum truck speed, that will depend on what is the design speed and also what is the logically the volume to capacity ratio. Because at low volume to capacity ratio, there may not be many vehicles which have to follow the slow moving vehicles, but as the volume to capacity ratio approaches unity, that means as the vehicle volume generally increases on road, it becomes more annoying and more critical consideration. Therefore, the speed value has to be considered, keeping this thing in mind, that generally it is more annoying when the design speed or when the volume to capacity ratio is higher. Now, studies indicate that it is observed from several studies that regardless of average speed on a road, the more a vehicle deviates from the average speed, the greater its chance of becoming involved in a crash. That is a very, very interesting and a very vital observation. The more that vehicle deviates from average running speed, more is the possibility of that vehicle to get involved in crash or accident. So, a common basis for determining critical length is based on reduction in speed of truck below the average running speed, because it is following, the basis is following. So, once it is mentioned that the more a vehicle deviates from the average running speed, more is the possibility of getting it involved in crash. So, therefore, now the critical, while we are trying to define or understanding the length of critical length of grade, then a common basis is recommended, that on the basis of reduction in speed of truck below the average running speed, control that deviation from the average running speed. Let us see. Traditionally, a reduction of truck speed of 25 km per hour has been used as a basis for obtaining critical length. However, the crash involvement rate is found to increase significantly if the speed reduction is more than 15 km per hour. It is observed that if we take a speed deviation of 25 km per hour and another speed deviation of 15 km per hour, in the first case the possibility of vehicle getting involved in a crash is 2.4 times almost higher. That means, as the speed deviation is more, instead of 15, it becomes 25, then the possibility of involvement of vehicles in crash becomes 2.4 times higher. That is a very, very vital observation. So, although earlier 25 kilometer per hour speed reduction was used as a limit for design or as a basis for design, based on these findings it is now revised and recommended as 15 kilometer per hour. Therefore, it is recommended to obtain critical length based on reduction in speed of 15 kilometer per hour, not 25 kilometer per hour. Now, here the graph shows as the length of grade increases and as the percentage of art upgrade increases, for various speed reductions how the curves will look like. It is obvious that if for a percentage upgrade, for a particular percentage upgrade, say if we take this one for a percentage upgrade, if we consider allowable speed limit as 15 kilometer per hour, then obviously the length requirement is something speed reduction. If we consider a higher speed reduction, say 25 or 30, say just for example, obviously a longer length of grade is acceptable. But normally taking 15 kilometer per hour as the speed reduction limit, the critical length of the grade is decided. Now, this value of critical length of grade will be lesser as compared to what was used earlier. That means, if we use 25 kilometer per hour as acceptable deviation, then obviously critical length of grade would have been higher. So, if we consider 15 kilometer per hour, it is lesser. Now, when an upgrade is approached on a momentum grade, that means there is a downgrade and then an upgrade. Obviously, even the heavy vehicles also probably can have a better speed profile. In this case, tolerable speed limit may be increased to account for higher approach speed for trucks. That means, earlier what we were using as the basis, say 15 kilometer per hour. Now, if there is a momentum grade, then the tolerable speed limit may be adjusted. Maybe instead of 15, one may take as 20, one may take this limit as 20 or the reduction is 20 kilometer per hour. This of course, is the designer's judgment. So, looking at the condition, the tolerable speed limit or increase speed reduction may be increased by certain amount for higher approach speed for trucks. That kind of adjustment is possible and can be done. Now, let us come to the curve design part. So, we have discussed the upper limits of grades, the lower limits of grades, and also the basis for deciding the critical length of grade as per AASHTO. With this background, now let us try to understand what should be the basis for design of summit and valley curves. We have already discussed in lesson 13 about summit curve and the valley curve and the rationality for design of those two types of vertical curves as per IRC approach. Now, we shall discuss about the AASHTO approach for design of summit and valley curves. First, let us talk about the summit curves. Summit curve design again it is basically the side distance that is the major consideration, and the side distance again may be stopping side distance or it may be overtaking side distance. Also, for each of these two cases, that means stopping side distance and overtaking side distance, the length of the curve may be more than the side distance available, or the length of the curve may be less than the side distance available. So, that means first thing, side distance is the major consideration. Side distance may be in terms of stopping side distance, which is the absolute minimum requirement. It may be overtaking side distance. Then in each case the length of the curve may be more than the available side distance, or it may be less than the available side distance. All these cases were covered when we discussed about the IRC approach. Now, basic formulations or basic equations, whatever were used or in whatever were used or mentioned during the earlier discussion when we discussed about the IRC approach, here also the basic equations are generally same. Let us see. Look at this equation, SST consideration and case 1 when length is greater than stopping side distance. In this case, this is the basic equation that may be used for calculation of the length of summit vertical curve. This is similar to what we have discussed or what we have indicated when we talked about the IRC approach. Basic equation is same, only thing here A is expressed in percentage, the deviation angle. So, this it is A by 100, there it was n, where n is essentially A by 100. Now, the final form A square by 658, this looks apparently different from what we indicated in terms of IRC approach, but in this case this value of capital H, that is height of driver's eye above road surface, as per ASTO it is 1.08, in IRC it was 1.2, and height of object is 0.6 meter, as per IRC it was taken as 0.15 meter. So, if we put the ASTO recommendation about height of driver's eye above road level and also height of the object, then it is a simplified expression like A square by 658. Similarly, for case 2 also, the equation, basic equation is like this as indicated here. Again it is same as what we indicated in IRC approach. It is basically same, basic equations are not different. Again appropriate value of capital H and small h if we put, then it becomes a simplified expression like this, L equal to 2s minus 658 by A. So, basic equations are same, the only difference is the height of driver's eye above road level and height of object, that is different as per ASTO. So, appropriate values are to be given, and also here the deviation angle is expressed in percentage. So, it is A by 100, in IRC we indicated it as n, the deviation angle. Now, if we come back to this equation, the rate of change of grade at successive points on the curve is a constant amount for equal increments of horizontal distance, and it is equal to the algebraic difference between intersecting tangent grades divided by the length of the curve. Simply A is the algebraic difference between intersecting grades or the deviation angle. That much deviation angle is negotiated over a length A. So, what is the change of grade? It is nothing but A by L in percentage per unit length. A by L percentage per unit length. Now, the reciprocal of this, that is L by A, is nothing but the horizontal distance needed to make 1% change in gradient. That means, what is the horizontal distance required to make a 1% change in grade? That means, per percent change in grade, what is the length of the curve that is required? This is termed as k factor. We say k, it is nothing but a measure of curvature. So, k is useful in determining minimum length of vertical curves for various design speed. We talk it k is L by A. Now, it is required or it is useful in determining minimum lengths of vertical curves for different design speed. Why for different design speed? Because for different design speed, the side distance requirement or the stopping side distance requirement is different. So, the length also will be different. Now, minimum length of vertical curves for different values of A to provide the minimum stopping side distance for each design speed are shown as exhibit in ASTO. ASTO gives exhibit showing the minimum required length of vertical curves for different values of A. Minimum length of vertical curves for different values of A, it will vary depending on the A, because length is k into A. Then again it will vary depending on the design speed, because the side distance requirements or the stopping side distance requirements will also vary depending on the design speed. So, ASTO gives the length of the curve as exhibit. Let us have a look at that. Look at this part or this graphs or exhibit. Now, solid lines, these are the solid lines you can see. These solid lines shown in white color are the minimum vertical curve lengths on the basis of rounded values of k. Observe that it is based on the rounded values of k. Now, what is rounded values of k? Actually, we know this expression L equal to A square by 658. We have already discussed that. Say it is for SST consideration and when L is greater than stopping side distance. In that case, the length of the curve can be calculated by this formula, simplified formula A square by 658. If we take this formula, then for different design speed, we can anyhow calculate the stopping side distance, that already we have covered earlier, how the stopping side distance can be calculated, that has already been discussed earlier. So, if the design speed is known, we can easily calculate what is the required stopping side distance, considering the reaction time and the deceleration design deceleration rate and all these things, we can calculate the required stopping side distance. Now, once the stopping side distance is known, that means this S value is known. So, if we know this column, then we can also calculate this value, stopping side distance values. Now, once we know S, then L by A is k. So, we can calculate what is the actual k value, which is nothing but S square, this side distance square divided by 658. If we do that, these are the calculated values. okay, for different design speed. Now, these values are rounded off. Say for example, it is 25.7, it is rounded off to 26. 73.6 is taken as 74. So, using this rounded values of k, these solid lines are drawn. So, you can see here it is k 7 for speed 70, k is 17, for speed 80, k is 26, like that. So, these are rounded values of k. See, this solid line gives the minimum vertical curve length on the basis of rounded values of k. Now, to the right of S equal to L line, you know there are two different formulas to calculate the length of the curve when it is L is greater than S and another case when L is less than S. So, this dotted line indicates when S equal to L. Right side it is S less than L, left side it is S greater than L. Now, what it is saying, that to the right side of S equal to L line, the value of k or the length of vertical curve per percentage change in A is a simple and convenient expression of the design control. You can obviously see these are basically just straight line equation. So, for every percentage change in grade, what will be the length of the curve or k value, that can be obtained very easily. It is a simplified expression, because if you take this dotted line which represents S equal to L, then the right side it is a convenient expression of design control, because these are essentially straight lines. The design control in terms of k covers all combinations of A and L for any design speed. Therefore, it is not necessary to define or to mention A and L separately. If we consider k, that covers all combination of A and L, and therefore, it is not necessary to define or to address A and L separately in design tables. Now, again where S is greater than L, that is left side of this dotted lines which represent S equal to L. So, this is S equal to L, essentially this side we are talking when S is greater than L, the computed values plot as a curve that bends to the left, and for small values of A, the vertical curve lengths are 0. When to the right side it is this expression A square by 658, to the left side it is this expression 2 s minus 658 by A. So, for small deviation angle, or if we try to use that equation 2 s minus 658 by A. So, that is the equation we are talking about. So, if we use that, then the theoretical curves to the left of this one, it actually takes a turn or it bends like this, as indicated by this yellow line. So, for v equal to 7 up to this point it is a straight line, then beyond that it is a dotted line as shown in this case. So, maybe for k equal to 80 also it may be something like this. Okay. So, it takes bend to the left side as per the formula. So, if we use the formula, then try to calculate the length, the lines will take a shape like this. and for obviously small length of A, the curve length may be 0 also. That means indicating that as such for small deviation angle, there is no need to provide a length of curve. But this is not a good design practice, because and that is why, so where S greater than L, the computed values plot as a curve that bends to the left, and for small values of A, the vertical curve lengths are 0. It does not present desirable design practice. You can again see that it is taking a turn to the left. So, it will be shape of that kind. Because it is does not represent desirable design practice, a minimum length of vertical curve is used. Now, the moment we say a minimum length of vertical curves is used, there are many approaches. Sometimes this is expressed as either a single value, sometimes a range of different design speed, sometimes as a function of A, but the general practice is to provide L minimum as 0.6 V. It is the general practice to provide minimum length of summit curve as 0.6 V, where V is the design speed in kilometer per hour and L minimum is the minimum length of curve in meter. Now, these terminal adjustments are shown as vertical line. Let us again go back to this, to that curve, right. So, theoretically it goes like this, it takes a bend, but from practical consideration we use some minimum limit, which is again a function of the design speed. So, these vertical lines are essentially showing those terminal adjustments. That is what should be the minimum one. Now, then this exhibit actually extend the line for S less than L, and it extends it up to that vertical line. That means, these are the limits, draw a vertical line here, extend this horizontal line wherever it meets. This total curve represents the required length of curve for that particular design speed. So, these terminal adjustments are made and then extended, this S less than L portion is extended to meet the extended vertical lines. That way this whole exhibit is developed. I have mentioned it again once again, design values of k when S less than L can be used without sufficient error, where S greater than L by extending diagonal lines to meet the minimum length vertical lines, and this results in appreciable difference from the theoretical calculation only when A is small. So, if we take the draw the theoretical curves that takes a turn towards the left and that gives value even 0. So, this vertical terminal adjustments are made. Now, appreciable difference is obtained from theoretical calculation only when the deviation angle is very small, and obviously for deviation angle, where deviation angle is very small, although theoretically we do not need probably any length of vertical curves, but it is not a good design practice and we want to use some minimum length of vertical curves. So, that way this overall things become acceptable. So, the difference from theoretical only when A is small and little or no additional cost is involved in obtaining longer vertical curves. Now, that is one side. Now, let us look at that other component, that is from drainage consideration, which is again a very vital part. Now, from drainage consideration, a minimum grade of 0.3% should be reached at a point about 15 meter from the level point on type 1 curve. What is type 1 curve? Type 1 curve was like this. Okay. Now, this is the point where it is a level point. So, what it is saying, for type 1 vertical curve, from drainage consideration, a minimum grade of 0.3% should be reached at a point 15 meter from the level point on type 1 curve, just to facilitate drainage. Now, this if we consider, this corresponds to a K value of 51. This corresponds to a K value of 51. Let us go back to that exhibit. You can see here this K equal to 51 is also shown as a dotted line. This is from drainage consideration. That means, up to that point for type 1 curve, we should have K equal to 51 as the limit, not as a design limit. That discussion I will come back. So, maximum value of K for drainage is 51. If it is more than 51, that means it is much flatter, the grade is much flatter, or grade in general is flatter than what is required for drainage point of view. If K value is more than, so look at this exhibit again, to the right side of this dotted line. So, this whole area V equal to 100, 130, these all represent K value more than 51. That means, this is a range where the length of the curve, it is, or the grade is not appropriate for drainage consideration. Of course, if it is more than 51, then special care should be taken for drainage near the high points of such type 1 curves, because if K is more than 51, that means they are essentially flatter curves. So, therefore, special care is necessary for drainage near the high point of such type 1 curve. However, this K equal to 51 should not be used as a design limit. What all we are trying to indicate, that if it is more than 51, the K value, special attention is required for drainage, but it is not that K more than 51 is not acceptable. Certainly, it may be acceptable, but we have to keep it in mind that if it is K is more than 51, then special care or attention is required for drainage purpose. That is all. So, no need to consider K equal to 51 as a design limit. It only says that drainage to be designed more carefully when K is more than 51. Now, coming to OST consideration, again the basic formulation is same, only thing in this case the height of both capital H and small h should be taken as 1.08. So, appropriately one can get the required length. For L less than OST, again the same basic equation, only thing capital H or small h are same here. So, accordingly values are to be provided, but generally it is found that if the length is to be designed to provide adequate overtaking side distance, the length requirement is much higher. So, it is not practical to design summit vertical curves to provide required overtaking side distance. Most of the cases this is not designed for providing overtaking side distance. So, only SSD satisfying the requirement of SSD may be adequate. Now, length of valley curves, there are 4 different criteria that are considered. One is the first one is the headlight side distance, that is number 1. We have already discussed about this headlight side distance requirement during our discussion about IRC approach. Here also it is the same. 2 cases are considered when length is more than stopping side distance and case 2 is length is less than stopping side distance. We have again discussed these 2 cases during our discussion about IRC approach. It is exactly same, except the tail light height is different here and A is expressed in percentage, that is the deviation angle. So, putting the appropriate values, again here also this angle beam light beam angle is taken as 1 degree. So, accordingly you can get these expressions, also for these cases also one can get it. So, basic formulation is same, only thing ASTO specific design values are given. The formula basic formulation is same. Now, second criteria is passenger comfort. This also we discussed, but IRC normally this headlight side distance criteria dominates. So, therefore, design is done only based on the headlight side distance, because if it is safe for that consideration, it will generally satisfy the requirement of other things. So, passenger comfort is the another criteria what is considered. Changes in centripetal acceleration depends on vehicle weight, suspension system, etc. And when centrifugal acceleration does not exceed 0.3 meter per second square, it is generally considered as comfortable. So, according to that, if we take the general expression, then the length of the curve may be obtained like this. Similarly, for drainage control, this we have already discussed. For summit curve also, k equal to 51 presents a kind of limit, although we can go beyond that, and this is particularly for curved section, because curved section the drainage problem, the water cannot go directly onto the shoulders. So, for especially for curved section this is important, and here also k equal to 51 is used as a limit. Now, for general appearance is also considered another criterion considered for design. For small to intermediate value of a rule of thumb is used and length is calculated like this, L equal to 30 A. So, these are the 4 different criteria those are used. One is headlight side distance criteria, then passenger comfort, then drainage control and the general appearance. It is normally found that the headlight side distance appears to be the most logical criteria for general use, and of course, for valley curve also it is convenient to express the design controls in terms of k, as we have discussed in details about the summit curve. So, for valley curve also it is convenient to express the design control in terms of k for all values of deviation angle A. Now, design control for sag vertical curves are also given as exhibit in ASTO based on rounded values of k, as it is given for the summit curve. Similar type of exhibit is also available expressing it in terms of the rounded values of k. Longer curves are desired wherever practical, but special attention should be exercised where values of k exceeds 51. That means, special care is needed when value of k is more than 51, particularly considering the drainage part. Now, in the last class lesson 13, we talked about the valley curve. We told that comfort criteria could be a basis. Now, in this case let us quickly try to see that how we can calculate even the required length. In many textbooks in India the same approach is given and you can also calculate the length. Here the valley curve is considered as the two spirals, two transition curve without a circular curve in between. So, if L s is the length of spiral, it is actually L by 2, where L is the total length of the valley curve. So, radial acceleration is v square by r. You can get this radial acceleration from changes from 0 to v square by r over a time t. How we can calculate the time? The time is nothing but to cover this L s distance, which is the length of the spiral. So, if L s is the length, v is the speed, the time taken t is L s by v. So, rate of change of radial acceleration is nothing but v square by r by t, where t is L s by v. So, it becomes v q by L r. So, length becomes v q by L r. Now, value of r at length L s is nothing but L by 2n or L s by n, that we can consider. So, if we put these values, then accordingly you can calculate the length L s equal to n v q by c to the power half, and the total length L is 2 L s. That way we can calculate. Now, it is recommended the value of c may be taken as 0.6 meter per second cube. So, if we take that value of c, accordingly we can calculate what should be the required length considering the comfort condition. Although IRC says, and it is also found, the dominating criteria will be the headlight side distance criteria. Now, try to answer some of these questions. Define critical length of grade, discuss the basis recommended by AASHTO for obtaining the critical length of grade. Number 2, discuss the design controls for crest vertical curves as per AASHTO. Number 3, mention different criteria recognized by AASHTO for establishing lengths of sag vertical curves. Try to think about the answers, we shall discuss the answers in the next lesson. Now, let me quickly try to answer to the questions of lesson 13. What are the various types of gradient recommended by IRC? Ruling gradient, we should try to design it for ruling gradient. If the terrain does not permit, we can go up to limiting gradient, or case specific situation we can go up to limiting gradient where it is higher or steeper than ruling gradient. Under exceptional situation we can go up to exceptional gradient. Now, why the grade compensation is required? Because if horizontal curve is there and vertical curve is there, the component of tractive effort available in the direction of movement becomes lesser. If it is t the tractive effort, and if it is a horizontal curve, only the t cos alpha component is available. So, even if the grade is there, it is further a component. So, therefore, a kind of grade compensation is required for smooth operation of vehicles. Now, a vertical curve is formed at intersection of two grades, 4% and minus 4%. So, this is clearly case of the summit curve. One can calculate what is the required stopping side distance, then the deviation is the algebraic difference. So, 0.08. Let us assume L is greater than SST, accordingly n square by 4.4. We calculate the length, which is 298, which is greater than 128. So, our assumption is correct. So, that way we can calculate also the length of curve. Now, why traveller's discomfort is considered only for the design of valley curves? This answer is simple. The centrifugal force and gravity force, they are acting in the same direction. That is why only for this kind of valley curve it is considered. In summit curve they are acting in opposite direction. So, there is no problem of discomfort. Thank you.